సో సార్ ఓకే సార్, ఎవ్రీథింగ్ ఈజ్
హలో
ఫైన్.
సార్.
సార్
వినిపిస్తుందా
యూట్యూబ్
సార్?
లింక్ కూడా స్ట్రీమింగ్ కరెక్ట్గానే అవుతుంది.
ఓకే సార్.
రైట్ సార్. ఒకసారి మీ ప్రెజెంటేషన్ చెక్ చేయండి సార్. మీకు ఒక్కరికే ప్రెజెంటర్గా నేను యాక్సెస్ ఇస్తాను అలా అయితే.
సార్ సార్ యాడ్ చేయమంటారా, షేర్ చేయమంటారా?
చేయండి సార్ ఒకసారి చూడండి. ఓకే సార్, ఎవ్రీథింగ్ ఫైన్.
రైట్ సార్. ఓకే సార్, సెషన్ స్టార్టింగ్లో షేర్ చేస్తాను సార్.
సెట్టింగ్స్లో అదే చూస్తాను సార్, మీకు ఒక్కరికే ఇచ్చేటట్టు.
ఒక 1 or 2 minutesలో నేను వస్తాను సార్. మళ్ళీ ఇప్పుడే వస్తాను.
ఓకే సార్. Welcome of the chief guest on behalf of the Department of Civil Engineering, GMRIT. I welcome our today's guest lecture speaker, Mr. T. Srinivasarao, who is a research scholar in IIT Bombay in remote sensing and GIS, most renowned అవసరం లేదు. He is previously worked as an assistant professor అని చెప్పుకుంటూ వెళ్ళిపోతాం అంతే. అతని గురించి చెప్పిన తర్వాత we are grateful to him for accepting our invitation and becoming a guest lecture speaker of today's event అని చెప్పేస్తాం ఒక మాట అంటే. ఓకేనా ఓకేనా నోట్ డౌన్ చేసుకో, అవసరం అయితే గూగుల్లో సెర్చ్ చేయి. నాకు డీటెయిల్స్ చేస్తాను. ఒక విషయంలో ఏదైనా తీసుకెళ్ళి ఇదైనా పర్వాలేదు. ఫస్ట్ ఆఫ్ ఆల్ ఐ వుడ్ లైక్ టు గుడ్ ఆఫ్టర్నూన్ టు ఆల్. Good afternoon to all. First of all, I would like to thank you from some and మాట్లాడేసిన తర్వాత నేను I would like to thank each one of you for joining this one day, otherwise joining this online virtual guest lecture on one day joining this virtual guest lecture on applications. లేకపోతే దాని బదులు తీసుకోవాలి, బాగుంది ఎందుకంటే గెస్ట్ నేమ్ కూడా వస్తుంది. I'm thoroughly pleased to witness you all here in this virtual guest lecture. It's my privilege. It's my privilege to address you all on the behalf of all the participants in this lecture. Sir, అలాగే పర్వాలేదు. Guest lecture, workshop కాదు, guest lecture. It's my privilege to introduce on behalf of the guest lecture ద్వారా రాసా కదా తీసేసి on behalf of the civil engineering department I welcome our chief guest speaker. I welcome our guest speaker Mr. T. Srinivas Rao. Chief, this is a guest speaker. Guest speaker. Guest lecture speaker. Speaker T. Srinivas Rao. Right. Students in tower joining. ఏమ్మా జాయిన్ అవ్వండి అమ్మా టైం అయిపోయింది అక్కడ స్పీకర్ 15 minutes ఇదే జాయిన్ అయిపోయారు ఇంకా స్టార్ట్ చేయలేదు మీరు జాయిన్ అయితే స్టార్ట్ చేయొచ్చు ఫార్మర్ అని పెట్టేయండి ఫార్మర్ అండ్ కాకుండా ఇక్కడ వరకు పెట్టేసి ప్రీవియస్లీ వర్క్డ్ యాజ్ ఎన్ అసిస్టెంట్ ప్రొఫెసర్ previously worked as a as an assistant professor as an assistant professor in VMR visa ID. Okay, దాని తర్వాత అతను ప్రొఫైల్ మొత్తం చదివేస్తాను. Currently he pursuing PhD at IIT Bombay and he received his BTech from IIT Bombay in remote sensibility course and also he received his BTech graduation from the University College of Engineering Sri Venkateswara University Tirupati. Okay, he is having 5 years of teaching more than 5 years of teaching experience. He also received grants from the he is also received some grants to solve the real-time projects related to remote sensing and GIS and GIS. ఓకేనా జనరల్గా చెప్పింది అంతే మీరు జాయిన్ అవుతుంది మీ లాగిన్ నుంచి డైలీ ఎందుకు అది ముందుకు చదివేయడమే నీకు ఇక్కడ ఏం కనబడవు కదా వీడియో ఆన్ అవ్వదు ఇదేమని వస్తుందమ్మా మేము హలో సార్,
సార్.
స్టార్ట్ చేద్దామా సార్?
సార్.
ఇక్కడ నుంచి ఇచ్చేసిన ఇక్కడ నుంచి చెప్పేసిన పర్లేదు, అది మీకే పెట్టేసి ఓకే బెటర్ కదా. శ్రీనివాసరావు, who is a PhD, who is an honors on PhD or a PhD. This engineering department, I welcome our chief lecture speaker, Srinivasrao, who is a PhD scholar from IIT Bombay and previously worked as assistant professor in Vienna region more than 5 years. He has a teacher experience of 5.5 years. He is considered one of the 3 members who received funding at the conference. Education details. He also published various journals in national conferences, international and national conferences, and journals in GIS, general statement. Okay. Start. ఒక 2 minutes నేను ఇంటిమేట్ చేస్తాను. ఏమో 29 మెంబర్స్ జాయిన్ అయ్యారు, మిగతా క్లాసు. ఓకే 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 ఫైన్, సరే సరే, నో ప్రాబ్లం. ఓకే 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 రైట్. ఇచ్చేసాం, ఇంట్రడక్షన్ ఇచ్చేసాం. రికార్డ్ అవుతుంది.
Good afternoon, everyone. First of all, I would like to thank each one of you for joining this virtual guest lecture on applications of remote sensing and geographical information system. I'm thoroughly pleased to witness you all here in this guest lecture on the applications of remote sensing and geographical information system. On behalf of this civil engineering department, I welcome our chief guest lecture speaker, T. Srinivasrao Garu, who is PhD scholar from IIT Bombay and previously worked as an assistant professor in Vienna Vignan Jyoti Institute of Engineering Technology. He has teaching experience of 5.5 years. Present, Srinivasrao sir is pursuing a PhD in IIT Bombay and completed MTech from IIT Bombay and completed BTech from SVU College of Engineering. He is considered as one of the 3 members who received funding at the conclave held by AIA, Hyderabad at Ideas Conclave 2019. He has published many journals, national and interjournal journals, etc. Thank you for giving me this opportunity.
Sir.
Sir,
Uh,
shall I go ahead then?
yes, sir. Yes, sir. Please present your PPT, sir.
Yes, sir. Yes, sir. Sure. First of all, I would like to thank you for the nice introduction, and a very good evening to all of you.
Good evening, sir.
Yeah, good evening. Good evening. Good evening. My screen, is it visible?
Yes,
Yes,
sir.
sir.
Yes, sir. Visible.
Yes, great. So there is no hiccup or anything in my audio as well, right? It is clear, right? Audio is also?
Yes, sir. Yes, sir.
Right, perfect. So first of all, I would like to thank Ramu sir for inviting me to present this session on application of remote sensing. So the title of the presentation, which is conveyed to you, that is application of remote sensing, it is very generic. Here I am going to be a little bit specific about the type of application which we are going to discuss here and why I choose this particular area. So that means that is cryosphere. So here remote sensing has got several applications in several fields. So you talk about climate, okay, you talk about climate, you talk about weather, surveying, so many fields are there, and remote sensing has got, just a second, somebody is trying to join. Ramu sir,
Sir.
మీరు యాడ్ చేయడానికి ఏదైనా వస్తుందా నేను కాకుండా?
Yes, sir. Yes, sir. I will take care about that, sir.
ఓకే సార్, లైక్ మధ్యలో నోటిఫికేషన్స్ వస్తున్నాయి. వితౌట్
ఓకే
ఓకే ఓకే
Okay, sir.
presentation is it still visible?
Yes, sir. Yes, sir.
Right. So here I would like to rewind just a little bit. So remote sensing has got so many applications in so many fields. So here fields in the sense, so we have climate, okay, so we have weather, we have surveying related things, and if we are talking very specifically, geotechnical engineering is there, okay. So what we can do in geotechnical engineering, soil moisture we can monitor. And what about climate? We can talk about events like rainfall, or simple studies about temperature, or you can even study about different layers of the atmosphere like troposphere and ionosphere, or whatever different layers that are there. But here I have chosen a simple field, that is not simple, not so simple, but here I have chosen a simple area. Here I have chosen an area, cryosphere, and I'm going to discuss what are different applications that you can work on with help of remote sensing. So let's go into this presentation. So here the agenda for today's session is going to be, first of all, I'm going to discuss what is cryosphere, then I'm going to discuss about a little bit basics about remote sensing as well, then how we can apply, or in which areas we can apply this remote sensing in this particular field of cryosphere. Okay, after that, if you have any questions, you can discuss about it. So okay, before going into the session, so does anyone know about cryosphere? I would like to call upon the audience. So anyone has heard about the cryosphere before this presentation?
No, sir.
No? At least someone, one person at least. Okay. So cryosphere is a Greek word, which means cold or too cold. And this cryosphere indicates coldest portions of the Earth's surface where water is going to be in the solid form. So water is in the solid form means water exists in the form of ice or snow. So water can exist in different forms. It can exist in the solid form, a liquid form, or even in the vapor form. But here in the cryosphere, water is going to exist in the solid form. That means we are talking about polar regions or high altitude mountain regions such as Himalayas. Okay, so these are the regions where water is going to exist in the solid form. Cryosphere indicates all these regions. So this definition is clear, I guess. Now, when I am talking about this cryosphere, I mentioned water exists in the solid form, but water can exist in the solid form in different ways. Here, different ways in the sense we call it with different names. So these things where water exists in a solid form forms the components of cryosphere. So here I have broadly classified. So we normally classify this cryosphere into 8 major components. First one is sea ice. Next, ice sheets, then ice shelf, iceberg, glaciers, permafrost, lake ice or river ice, then snow. So these are all different components or different features, varieties where water can exist in the solid form. Some of these components you already know. Probably you know about glaciers, icebergs, and snow. And anyway, we are going to talk about all these components very briefly one by one. So before that, where water exists in the solid form. So here you can see that this shaded region, cyan color shaded region. So this region indicates the major cryosphere region. So here we can divide this cryosphere into 3 major regions. One is Antarctica, second one is Arctic, and third one is extrapolar regions. So we know this North Pole and this South Pole where this Arctic and Antarctic regions are situated. Other than this northern and southern regions, so that means Arctic and Antarctic regions, wherever water exists in the solid form, it falls under the third region, that is extrapolar region. So this one is the northern part is northern polar region and southern part is southern polar region. And the other places, for example, if you are talking about India, it is neither situated in the upper band nor situated in the lower band, but it is at some different location. This here in India, where we see water in the solid form, can fall under this extrapolar region. So coming to the Antarctic cryosphere region, so basically it is surrounded by ocean, and 87% of the Earth's total ice is present in this Antarctic cryosphere region, and ice shelves contain 2.5% of the ice. So majority of the Earth's ice is present in this Antarctic cryosphere region. However, ice shelves contribute 2.5% of that ice. So we will talk about what is ice shelves as well. Next is Arctic cryosphere region. It is an ocean basically. However, it is surrounded by land. So you can clearly see in this picture. See, so Antarctica region. See, this is Antarctic region I mentioned, right? Here I mentioned it is surrounded by ocean. So this is the Antarctica region. And here, if you see the boundary, it is surrounded by the ocean. And coming to this Arctic region, so here normally ocean is in the form of solid here. Some parts of this ocean is in the form of solid and it is surrounded by the land. So
Srinivas sir,
most of the ice, sir,
sorry for the interruption. Slides are not changing, sir.
not changing, sir, like. mm, Now?
Starting slide visible, sir. Yes, sir. Okay, sir.
Change అవుతుంది sir.
Thank you, sir.
Right, sir. So these are all different components of cryosphere. Like I'll very quickly go through these things once again. So cryosphere is divided into different components. Basically, cryosphere indicates coldest portions of the Earth's surface where water exists in the solid form, and water can exist in the solid form in many varieties. So these forms are all these forms forms different components of the cryosphere. Hello, sir. Hello.
Sir, continue.
Okay, right. So these 8 components forms major components of cryosphere, that is sea ice, ice sheets, ice shelf, iceberg, glaciers, permafrost, and others. So these components are present in 3 different regions. Actually, cryosphere is divided into 3 major regions. One is Antarctica, next is Arctic, and the third one is extrapolar region. So these bands that are present in the upper and the lower regions, they are Antarctica and Arctic regions. If snow or ice related components are present anywhere other than this Arctic and Antarctic, so they fall under extrapolar regions or mountain regions. So coming to the Antarctic region, it is an ocean. It is surrounded by the ocean, and it contains major chunks of the Earth's ice. 87% of the 87% of the Earth's ice is present in this Antarctic cryosphere region. And in this Antarctic cryosphere region, ice shelves constitute 2.5% of its ice. And next is Arctic cryosphere region. It is an ocean surrounded by the land, and surface consists of sea ice mainly. That means frozen sea. Here in Antarctic cryosphere region, water exists in the solid form. That part we are very clear about. But here, that solid ice is made up of ocean, that is sea. So you can see in this picture. Here Arctic Ocean is present in the upper location. So this Arctic location, parts of this Arctic Ocean is frozen, and it forms the Arctic cryosphere region. And downward region, if you look at, so here Antarctica we have, this is also frozen component. So next is extrapolar cryosphere region. It contains only 0.5% of the Earth's ice, and it includes wide variety of these cryosphere components such as ice caps, mountain glaciers, snow, permafrost, etc. But the strange thing is, these 0.5% of the cryosphere, 0.5% of the Earth's ice has immense interaction with the humans. Because that Arctic and Antarctic regions, this northern place and this southern place, these are extreme climatic regions where very less number of people are residing. Hence, most of the interaction with the cryosphere happens with this 0.5% of the Earth size. And here I have given a small metric, that is 5.2 into 10 power 7 million square kilometer. It is not square kilometer. About 5.2 into 10 power 7 square kilometers of area is affected by seasonal snow activities such as frozen ground. So every year, close to 5.2 into 10 power 7 square kilometers of the area is affected by seasonal snow activities such as frozen ground. So this is how different components of cryosphere are distributed over the world. So you can clearly see, when it comes to the India, we have only snow cover and this pink region. Pink region means glaciers. So Indian Himalayan region constitutes 2 different components of the cryosphere. First component is the glacier, and the second component is snow cover. And when we look at other parts of the world, we have permafrost, glacier, sea ice, snow cover, different things are present. Okay. So we have seen different components of cryosphere. Now the important thing is why we need to study the cryosphere. So here I am not going to mention all those reasons. But if we look at the first reason, uh, if we assume density of ice as 917 kilogram per meter cube, and if entire ice over the Antarctica and Greenland is melt, sea level is going to rise by close to 60 meter. And sorry for the interruption. And so if you assume density of ice as 917 kilogram per meter cube, and if entire ice over Antarctica and Greenland is melt, sea level is going to rise by 60 meter over the entire Earth surface. So this is going to, sea level is going to increase by 60 meter. That means so many countries are under the danger of getting submerged. So it is very important. This simple reason itself is very, single reason itself is very important to study about the cryosphere. So other than this, I would like to show some small videos. Okay, I will show those videos at the end of the presentation. So moving on to different components of cryosphere. First component is sea ice. It is basically water frozen in the seas and oceans, and 7% of the world's oceans are always in the state of frozen. And thickness of the sea ice varies from 3 inches to 9 feet. Polar oceans are normally in the frozen state. And here, if you are talking about Arctic Ocean, their sea ice is very thick, and normally it will be in the range of 6 to 9 feet. And if you are talking about sea ice thickness, in northern horizon, sea ice has maximum thickness in the month of March and minimum in the month of September. And in the southern horizon, it will be minimum in the month of February and maximum in the month of September. So these are some of the pictures of sea ice. You can see how strong and how thick the sea ice will be. So there a polar bear is moving over this ocean region. This is basically actually sea, interior of the sea. But this sea is in the state of sea is frozen. That is why this polar bear is able to walk here. Next component is ice sheet. It is a glacial ice having more than 50,000 square kilometer area. So here you should think about what is glacial ice. Before talking about ice sheets, we should have an idea about what is glacial ice. The glacial ice means any ice sheet that has movement associated with it. It is a moving ice. If you have so much amount of ice accumulated on a mountain because of the gravity and normal downward slope, it will have some movement associated with it. That ice will slowly flow towards the downward region because of the gravity and as well as its mass and slope. And that type of ice is normally called as glacier ice. If such ice has an area of more than 50,000 square kilometers, it is called as ice sheets. And these ice sheets are bigger than ice shelves and glaciers. Like I said, glacier is nothing but moving ice, and ice sheet has an area more than 50,000 square kilometer. So ice sheet is normally larger than ice shelf and glacier. These ice sheets now are present only in Antarctica region and Greenland. So because of this global warming phenomena, so whatever ice sheets that are present earlier, they have started melting. Now only they are present in Antarctica and Greenland regions. So some of the examples and names for ice sheets are given below the slides. So Laurentide ice sheet, Chilean ice sheet, Patagonian ice sheet, these are present in Europe and America. Moving on to the next component, that is ice shelf and iceberg. So ice shelves are firmly attached to the land and is a floating extension of the land ice. So the snowfall takes place over the land as well as the ocean bodies. And whatever snow that has fallen onto the land, if weather and climate supports, it will exist in the solid form for a very long time. And because of which this fallen snow will convert into ice, then into a small sheet of ice. And here ice shelf means it is an ice sheet or a sheet of ice that is attached to the land, and it has some extension which is floating into a water body. So an ice shelf is nothing but a ice sheet that is attached to the land and has an extension into the water body. So Antarctic continent is surrounded by the ice shelves, and icebergs are formed by calving of ice shelves. Calving means breaking of these smaller ice sheets. So if an ice sheet breaks, icebergs are formed. So icebergs are formed by calving of these ice sheets and glaciers into the oceans and other water bodies. Only 5 to 10% of the iceberg is seen above the surface of the water body. This is interesting thing. So 90%, close to 90% of the iceberg is submerged or present underneath the surface layer of the water body. So what we see on the surface is very small fragment of the iceberg. So masses of ice covering less than 50,000 square kilometer are called as ice caps. So this is a small, simple picture of iceberg. So another picture of iceberg. You can clearly see at the mountains. There is so much of snow and ice is present. Where this land is meeting the water body, there some type of attachment is present between the ice and water. And if temperature keeps on increasing, normally seasonally temperature varies because of the seasonal phenomena as well, because of the seasonal change in the temperature also, this ice, whatever that is present between the intersection of land and water, it will melt, and the bond will eventually loosen, and it will calve into the water body, which forms icebergs. So these are all icebergs which have formed at the intersection of this land and water body and have eventually floated into the interior parts of the water body. Another picture of iceberg. Next is glacier. As I said, it is a moving ice. However, the word is derived from both French and Latin. So it is a large body of perennial ice which moves over the land. It is formed when accumulation of snow and ice exceeds the ablation over a time. So glacier is formed when accumulation of snow and ice exceeds ablation. So snowfall is a continuous phenomena at certain regions of the world. When accumulation of the snow exceeds ablation, that means if snowfall is if the amount of snow that is accumulated is more than the amount of snow that is melt, then a glacier will be formed. Lot of snow will be accumulated, and because of the gravity and mass, it will slowly start moving towards the downward slope region. That's how glacier will be formed. These glaciers are the largest reservoirs of the fresh water. So we normally think this precipitation and underground water, I mean like underground groundwater as a major reservoir of fresh water. But the reality is different. Here glaciers serve as the largest reservoirs of the fresh water. So many perennial rivers, they originate from the glaciers. You talk about Brahmaputra, this is also originated from the glacier. These cover large areas of polar regions and mountain regions and are found in all continents except Australia. So this is a nice picture of a glacier. You can clearly see how ice is present at on the slopes of the mountains, and this accumulated snow will have certain movement associated with it because of the slope that is present as well as the mass that is associated with the accumulated snow. Next comes permafrost. So it is the largest component. So glacier forms the largest reservoir of fresh water, and permafrost forms the largest component of the cryosphere in terms of area. 20% of the Earth's surface is covered with permafrost, and it covers 54 million square kilometers of exposed lands of northern hemisphere. A permafrost is formed normally when the mean annual air temperature is less than -1 to -2 degrees Celsius. And if mean annual air temperature is less than -7 degree for 2 years, then permafrost is going to be a permanent thing. It is going to be a perennial thing. So consistent low temperatures draw the thermal energy from inner layers of the Earth's surface, freezing the water that is within the soil. If the air temperature over the ground surface is very less, let's say -5 degree. So we know how energy transfers from one location to another location. Always energy tries to form the equilibrium. In the inner layers of the earth, there is assume there is a good amount of energy compared to the outer regions. Then what will happen is the energy from the inner layers of the earth will slowly move towards the upper layers, then into the atmosphere, because of which the energy will be withdrawn from the inner layers of the earth. If the energy is withdrawn from the inner layers, then whatever temperature that is present in the interior layer before, that will keep on decreasing, that will kept decreasing, and because of which the water in the soil will present in the state of solid. So that's how permafrost is formed. Permafrost is nothing but frozen ground. Ground is in the state of solid, I mean frozen state. Whatever moisture or liquid that is present in the soil, that will be in the state of frozen. So coming to the permafrost, thawing of permafrost is a serious problem. That means melting of permafrost. If temperature increases, the the energy withdrawn will not happen, and slowly energy transfer will happen into the inner layers of the earth, and because of which whatever water that is present in the solid state earlier, it is going to melt. And this is going to be a serious problem, because these permafrosts are natural reservoirs of the carbon, and by melting, by thawing, this will be released into the atmosphere, particularly in the Himalayas, Central Asia, Tibet, Karakoram regions. This thawing of permafrost is a serious problem. So this is a simple picture of permafrost. Next is lake ice or river ice. Frozen bodies of ice, frozen bodies of rivers and lakes due to the seasonal temperature forms. These lake ice and river ice, they normally don't have any global level climatic significance. These are normally seasonal things. Like if winter comes, the temperatures will drop. Whatever lake or river that is present in that region, it is going to solidify. So hence it has only regional level climatic significance. And by studying the freezing and melting process events of these lake ice and river ice, it is possible to study how the climate is changing or how the weather is changing on a small scale. It is also very important to monitor, as they serve, as they are very key indicators in studying water balance of alpine regions and also in disaster management applications. So study of lake ice and river ice are very important in water balance of alpine regions as well as disaster management applications. So probably you know about the Kedarnath incident. So it happened because of a lake that has burst, glacial lake that has burst. So I will show you a small video at the end of the presentation. So this is a picture of river ice. You can see how the water is in the state of water is water is very dense, and so much ice is floating over the water body. So this is river ice. Finally, snow. It is the second largest component of the cryosphere in terms of area. So the first component is cryosphere, and the second component is this snow. It covers close to 47 million square kilometers of area. So though I have mentioned 47 million square kilometers, it varies seasonally. Snow cover is dynamic and it varies seasonally. So snow cover over the northern horizon varies from 3.8 million square kilometers to 46.5 million square kilometers during January to August. So when the summer is there, the amount of area that is covered by will fall to 3.8 million square kilometers. And when the winter is in its peak, the amount of area that is covered by snow will increase up to 46.5 million square kilometers. So this is not a square kilometer, it is million square kilometer. Okay, so it will increase up to 46.5 million square kilometers. That means what is happening? This 46.5 million square kilometers of area that is covered with snow, it contributes to so much amount of water, it contributes to so much of runoff during the remaining months of September, August, and etc. So snow is one of the major component which contributes to the uh, fresh water So this is a picture that is taken at Kulu Manali. You can see how thick the snow cover is. So now these are all different components of cryosphere. I hope these components are clear to you. If you have any doubt with regard to any of these components, you can ask me. Otherwise, we'll take the questions at the end of the presentation. Shall I go ahead here?
Yes, sir. Continue, sir.
Right. So now we have talked about what is cryosphere, what are different components of cryosphere, and though we have not discussed why one needs to study this river ice or lake ice, or why one needs to study about this ice sheet or iceberg or any other cryosphere component for that case. So it is very important. Only one major reason we have discussed. If ice, whatever ice that is present melts, sea level is going to increase, and increase in sea level is going to be a disastrous for many countries because they are under the danger of getting submerged. This is just one factor why we should study cryosphere. There are so many other factors. They have the capability to influence the weather patterns that are present in all countries, and they have the capacity to influence the ocean currents. So many things can be affected by these cryosphere components, which are to be studied and which are already in study. If you are interested, you can explore as well. But if you look at the problem, these cryosphere components are present in extreme climatic zones. If you look at this picture, for example, so you can see how thick the snow is, and the temperature is going to be very, very less. And in case if you want to perform any study, or in case if you want to get any measurement, it is going to be very, very difficult. You need to carry the equipment in such harsh conditions, and often equipments will not work because of the extreme climate, that is extreme weather that is present over there. Further, carrying the equipment onto those high altitude regions and performing the experiments is going to be very tedious task, as well as and dangerous and life threatening in many situations. So we require a technique with which we can get all the studies, which we can get the observations of these different cryosphere components in a convenient manner, and remote sensing has the capability to do that. So we should explore what is remote sensing and how remote sensing can be used for studying these cryosphere components. So I hope you are already going through this course of remote sensing course in your BTech. However, I am going to discuss few basics of remote sensing in a very quick manner. Then we will discuss about few applications as well. So as you can see from this picture, sun is a natural source of energy, and energy moves in all directions. Energy propagates in all directions from the sun. So while it is propagating, it will interact with different components of the atmosphere as well as on the Earth's surface. On Earth's surface, it interacts with objects such as buildings or roads, water bodies, grass, trees, etc. And in the atmosphere, it will interact with the different particles of dust or vapor molecules or gaseous molecules, etc. So whatever energy that is propagating from the sun, it will interact with the um, objects, intermediate objects such as atmosphere as well as earth surface objects. While they are interacting, different kind of phenomena will happen. So here different kind of phenomena in the sense, some amount of energy is completely absorbed by the objects, whereas some amount of energy is scattered into a different direction by the object, and some amount of energy will be reflected back into the atmosphere. Like that, the energy that is coming from the sun will be transferred into different directions after they interact with the different earth surface as well as atmospheric objects. This transferred energy, this shifted energy, this energy which is transferred into different directions will be captured by a sensor that is mounted on the satellite. These satellites carry the sensors. These satellites serve as a platform for the sensors, and these sensors will capture the energy that is flowing towards it. And this captured energy will be studied to understand how different objects are behaving, how different objects are changing. So this is basically how remote sensing is performed. So to simply put it in a definition, it is a science of obtaining information without getting into contact with any of the target objects using sensors and electromagnetic radiation. So here one doesn't need to come to this location where the road is present. You simply require a photograph of this road to talk something about talk something about its condition or its width or any other aspect. So remote sensing provides us a tool, provides us a way to do this, to perform this measurement and observation of different objects without actually going to those locations and objects. So remote sensing is the science of obtaining information without being in contact with any of the objects, with help of the sensors and the electromagnetic radiation that is naturally coming from the sun. So this entire process, what we are talking about here is termed as remote sensing. Of course, in remote sensing, there are multiple techniques such as such as optical remote sensing, microwave remote sensing, and hyperspectral remote sensing. Further, passive remote sensing, active remote sensing. So many techniques are there, but to simply put up, so this is what is happening at a broader level. But why remote sensing? So these are conventional way of performing the observations or conventional way of taking the measurements. One has to go to the field to collect the observations. For example, if you want to study the condition of the crop, whether the crop is healthy or not, is it under any stress? Though our main idea in this presentation is about cryosphere, remote sensing has the capability to provide us the information or observations in many fields. Here in this photograph, some people are collecting some observations that are related to the crop. So maybe you are interested in studying about the crop health, whether the crop is under any stress, is there water stress or some other nutrition stress you want to study about. To do that, you have to go to the field, then you have to conduct some experiments and collect some observations from there. And if you are trying to perform this type of study over the entire country or over the entire state, so you require so many people, as well as as well as so much of equipment and the things. And this observation is not going to get completed in a short span of time. So we require a science or a technique where we can collect all this data in very short span of time over a larger area, and remote sensing provides us that facility, that feature. So this is how observations are taken in snow fields. So you can clearly see a person digging a pit and crawling into the pit for collecting observations that are related to the snow. So this is going to be kind of exhausting because they have to carry the equipment at the same time. They face a lot of threat. So in cryosphere, it is going to be very difficult to conduct these experiments. And with remote sensing, and why remote sensing? So first thing is conventional data collection is inconsistent. So today I will go to the field and I will collect the measurement. Tomorrow some other person will go to the field and he will collect the measurement. Since here two different people are involved for collecting the same measurement, the way in which we perform the experiment may not be exactly same, because of which the observations may not be 100% comparable. They can be inconsistent, and because of equipment condition also, the observations could be inconsistent, and the manual observations provide very limited coverage. Often you have to carry the observations in observation studies in harsh conditions, and Most of these observations are very discrete. They do not provide a continuous or specially covered observations. So another picture of conducting field study in Cryosphere region. And with help of remote sensing, it is possible for us to have the global coverage in a repeated manner and in all weather conditions. Also, you can collect the data. Further, it is a cost-effective process when you are comparing it with the manual data collection over a larger time frame and a larger area. Further, it also provides continuous data collection, and data collection is going to be very consistent because no manual intervention is present here, and the equipment whatever that is present, it is not going to be disturbed normally. So remote sensing offers all these advantages, because of which we should employ remote sensing. So actually, this picture also tells some other interesting aspect. Here, if you see, there are so many satellites that are surrounding the Earth's surface, and each satellite has not, I mean, like different satellites have different capabilities. Different satellites work in different electromagnetic radiation ranges. So they offer different types of data to study the same feature. If I'm talking about a small region over Vizag, a small region over Vizag. Let's talk about the that Vizag beach only. If you are studying about that Vizag beach, here that beach will be covered by so many satellites. It will be pictured by so many satellites. So, for example, QuickSat, Landsat, Grace, IceSat. So many satellites are there, and these satellites work in different electromagnetic wave ranges. So they provide different types of data for studying the same area. Since you have different types of data, you can study for different purposes. It is possible for us to study, I mean, it is possible for us to take different types of studies as well with help of remote sensing. Coming to the history of remote sensing, earlier pigeons, kites, and balloons were used to conduct the remote sensing. However, nowadays we are using ground-based platforms such as tripods, moving vehicles, and towers, and helicopters, drones, satellites, and space stations for conducting this remote sensing. And this remote sensing basically includes mission plan, choice of sensors, reception, recording and processing of the signal, and then analysis of the resultant data. Mission plan in the sense, so what is the purpose of your satellite mission? You want to study about cryosphere, or you want to study about the rainfall, or the satellite is being launched for communication purpose. That has to be decided first of all. Then according to the your target or your motive, that means mission plan, you do the choice of sensors. You will select the sensors and you will design the sensors. Once this is done, once the mission plan and choice of sensors is done, it will be, the satellite will be prepared and it will be launched, and then data reception, data recording, and processing of the recorded signal will be carried out. So after processing of the recorded signal, we will be having certain amount of data. By analyzing this collected data, we will get some sort of results. So remote sensing includes these things. So as you normally read from the textbooks or any other sources, so these are different components of remote sensing: energy source, atmosphere and radiation, then interaction with the object, recording of the energy by the sensor, transmission and reception of that recorded energy onto the ground stations, then processing and interpretation of the recorded signal, finally application. So these are all different components of remote sensing. So this is electromagnetic spectrum. Here if you see, if you see this band, on x-axis we have frequency of the electromagnetic radiation. So frequency of the electromagnetic radiation. And on y-axis, we are talking about transmittance, atmospheric transmittance. For example, if I am talking about this 0.4 to 0.7 micrometers wavelength energy, this particular region which is not shaded here, this particular region which is not shaded here, let me show it to you. This region, okay, this region which is not shaded here. So it falls under visible portion of the electromagnetic spectrum. So why it is called visible energy is because the energy that is coming from the sun is not absorbed, or the atmosphere acts as a transparent layer for the incoming energy in zero point 0.4, in between 0.4 to 0.7 micrometers wavelength region. So the energy falls onto the earth's surface in between 0.4 and 0.7 micrometer, and it will interact with the earth's surface objects, and it can revert back into the atmosphere in this region. Whereas if I talk about X-rays, X-rays will also be coming from the Earth surface. But these X-rays, ultraviolet rays, these are completely absorbed by the atmosphere. Atmosphere will not transmit these portions of the electromagnetic spectrum onto the Earth surface. That's why there is zero atmospheric transmittance here. So those regions where atmosphere is transparent to the incoming energy are called as atmospheric windows, and these regions are essential for carrying out remote sensing. If you want to perform remote sensing in X-ray region or ultraviolet region, it is not possible because first of all, because there is no energy that is being transmitted to the earth surface. We require the energy to interact with the earth then only we can study about that object. Energy has to interact with the earth surface object, and after interaction it has to transfer back into the atmosphere, and that transferred energy will be collected by the sensors, which in turn generates a signal, and that signal will be studied for different applications. So none of this will happen in this X-ray or ultraviolet region because atmosphere is not transparent in that region. But in visible region, near infrared region, thermal region, microwave region, atmosphere is semi-transparent to completely transparent. So it is possible for us to study different Earth surface objects using remote sensing by conducting remote sensing in those wavelength regions. So these are simple spectral reflectance curves. So different objects interact differently with incoming electromagnetic radiation, and this incoming electromagnetic radiation is characterized by wavelength. So here you have 0.4 micrometers wavelength energy, 0.6 micrometers wavelength energy, 0.8 micrometers wavelength energy, and so on. If I'm talking about only 0.4 micrometers wavelength energy, this 0.4 micrometers wavelength energy will fall onto some of the 0.4 micrometers wavelength energy will fall onto a water body, vegetation, as well as soil. However, the way these three different types of objects interact with 0.4 micrometers energy is going to be different. When 0.4 micrometers energy, when this energy falls, this wavelength of energy falls onto a water body, less than 5%, less than 3% of the energy will be reflected back into the atmosphere. Whereas in case of vegetation, close to 5% of the energy will be reflected back into the atmosphere. Whereas in the case of soil, close to 15% of the energy will be reflected back into the atmosphere at 0.4 micrometer wavelength region. Similarly, you can study how these different objects are interacting at different wavelengths of electromagnetic energy. That is at 0.6 micrometer, 0.7 micrometer, 0.8 micrometer. What is happening with the different types of objects? So once you plot the graph for these interactions, you get spectral reflectance curves. These spectral reflectance curves are just like signatures. They are signatures. Okay, so like our signatures are different, these signatures are also different for different objects. With help of spectral reflectance curves, it is possible for us to differentiate between different objects. We can form spectral reflectance curve and we can differentiate between different objects. So one more key point here is, if you want to differentiate between vegetation and vegetation and soil, and if you perform remote sensing, if you collect data at 1.3 micrometer wavelength range, what is happening at this 1.3 micrometer wavelength range? At 1.3 micrometer wavelength, both soil and vegetation, they are reflecting 40 to 45% of the energy back into the atmosphere. So really you cannot differentiate between what is soil or what is vegetation. But if you capture an image, if you capture a signal at 0.8 micrometer wavelength or 1 micrometer wavelength, so dry soil is having close to 38% of reflectance, whereas vegetation is having close to 45% of reflectance. You try to quantify the reflectance at 1 micrometer wavelength, then looking at the variation in this reflectance, you will be able to distinguish between vegetation and soil. So these are different spectral reflectance curves for different forms of water. Since we are talking about cryosphere, so the peculiar thing about water is water can absorb almost all of incident energy on it. Here you can see very less amount of reflectance is there in between 0.4 and 0.8. After 0.8, there is no reflectance at all. Even between 0.4 and 0.8, very less amount of energy is being reflected into the atmosphere. What is happening to the remaining energy? It is being absorbed or transmitted into the other objects. So we see only very less amount of reflectance from the water body, clear water body to be precise. But here if you see this snow, fun, glacier ice, dirty glacier ice, these are all different variations of water body. If water body is in the state of if water body is in the solid state, if water body is in the solid state, then snow will be formed, or ice will be formed, or firm will be formed. So you see here, these different types of water bodies have different amounts of reflectance. So which is very important for us to study. So last thing what I want to discuss in this remote sensing part is a resolution. So there are different types of resolutions. While we are talking about remote sensing images, so we talk about spatial resolution, spectral resolution, radiometric and temporal resolution. Spatial resolution talks about size of pixel on the ground. So remote sensing provides us data in the form of images or signals, and each image constitutes so many number of pixels, and the amount of area that is occupied by a single pixel on the ground is termed as spatial resolution. And the spectral resolution, it is a number of wavelength bands and wavelength bands width. For example, if you see here, sensors have the capability to distinguish the energy based on the wavelength. So if I'm talking about Landsat MSS, multispectral scanner, okay, so and if I'm talking about the energy that is flowing towards multispectral scanner, all types of energy will be flowing towards multispectral scanner, because so many types of objects are present on the earth surface, such as water body is there, vegetation is there, soil is there, some other object is there. All these objects reflect different forms of energy into the atmosphere. So the incoming energy towards the multispectral scanner will include all wavelengths or multiple wavelengths of electromagnetic radiation. But this scanner is sensitive only to the some parts of visible region, near infrared and thermal infrared region. If some microwave energy is coming towards a multispectral scanner, it will not detect. It will only detect infrared and visible components of the incoming electromagnetic radiation. And even in this visible and infrared radiation, it can categorize that into different bands like green, red, near infrared and thermal infrared. So spectral resolution talks about that number of wavelength bands and what is the wavelength region in which the sensor is sensitive to. And then radiometric resolution, how many number of energy levels the quantified energy will get resolved into. The number of different gray levels the energy will be resolved into is termed as radiometric resolution. And temporal resolution is nothing but repeativity. After how many days the sensor will observe the same area under the same geometrical conditions, that is termed as temporal resolution. Now moving on to the different applications in Cryosphere. So I'll try to wind up in the next 10 minutes, 10 to 15 minutes. First application of remote sensing in Cryosphere is snow cover mapping. So snow, see, snow normally appears in the white color. Snow normally appears in the white color. And here if you see, by observing this snow color with other objects color, For example, mountain is in the dark brown color or vegetation is in the green color. It is very easy for us to identify what is snow and what is not snow. Okay, so snow cover mapping can be simply, very easily carried out using imagery. It appears so. It is not easy. It appears like with help of imagery, it is possible for us. It is very much possible for us to differentiate between what is snow and what is not snow, because snow cover has very high reflectance. If you see here in this picture, fresh snow has close to 100% reflectance, and in the previous slide if you see the water body has less than 5% of reflectance, but fresh snow has close to 100% reflectance. 100% reflectance means all blue component of energy, green component, red component of energy, all these components will get reflected uniformly, and by combination of these reflectance you see white color. So that is why this snow appears in the bright white color. But the problem with this type of simple visual analysis for identification of snow cover is you cannot differentiate between what is snow and what is cloud, because cloud cover is also in the form, cloud color is also white. So if snow and cloud are present next to next, you cannot differentiate between what is snow and what is not snow. But here in remote sensing, we can differentiate them using a technique called NDSI. NDSI offers us a way to differentiate between what is snow, what is not snow, and also vegetation. So NDSI is a ratio technique using which we can delineate snow covered regions from cloud and other objects. Now we have discussed some amount of information about snow. Snow is precipitation in the form of tiny ice crystals. Dry snow is nothing but a mixture of ice particles and snow, and wet snow is nothing but a mixture of ice particles, air, and liquid water. And there are different snow parameters such as density, wetness, snow depth, snow water equivalent, snow cover area, etc. So here we are simply talking about snow cover mapping. But see here in this slide, we are talking about snow density. What is the snow density? What is the amount of water that is present in the snow? How much amount of water we can get if that snow is melt? And what is the thickness of the snow? And how much area is covered with snow? So many things are there. Each snow physical parameter offers us a new research problem to work on. One can work on estimation of snow density. One can work on determination of snow wetness. One can work on estimation of snow depth, etc. So this single component of cryosphere, that is snow, it itself is presenting so many challenging questions for us. So all these questions we cannot it is very difficult to study with the limited amount of ground observation stations and data that is available for us at the moment. So we have to rely on remote sensing techniques which offer a wide variety of data and with a huge ground coverage. So like I said, we can use NDSI technique for differentiate between snow and cloud. So here if you see this picture, between 1.5 to 1.7 and 2.1 to 3.5 micrometer, that means in this region 1.5 to 1.7 and 2.1 to 2.35 in this region. Okay, so snow is present in the form of blue lines here. Snow reflectance is depicted by these blue curves, and ice clouds are depicted by this green curves, and water clouds are depicted by this red lines. So in visible region between 0.4 and 0.7 micrometer, that means in this region 0.4 to 0.7, in this region, if you look at the reflectance of this snow, water and ice, they are very close to 100%, almost 80 to 100% of the reflectance is present for all snow, water cover and ice cloud in the visible region. Okay, whereas if you see in between 1.5 and 1.7 micrometer, this snow has lesser amount of reflectance compared to the clouds, and same type of thing is present between 2.1 and 2.35 micrometer wavelength region. Snow and cloud reflectances are varying. So using this variation, so researchers have developed an index that is at green wavelength and short wave infrared wavelength. so which is called NDSI. This NDSI offers us a way to differentiate between what is snow and what is not snow. And next is glaciers mapping. So we have talked about what is glacier, and in glacier again so many problems are there, so many things are there. So different components of glaciers include head wall, zone of accumulation, crevasse, plucking zone, abrasion zone, terminal zone of the glacier, and there are other things as well, ablation, other things as well. So all these features and all these things required to be monitored for different applications. Some of the important zones of glaciers are present. Hello. Hello.
Sir. Sir, continue.
Okay. Some of the different zones of glaciers are present in this picture, such as accumulation zone, ablation zone, crevasse, lateral moraine, terminus, etc. So all these glacier zones can be mapped using remote sensing data. So this is a simple picture. This is a simple picture, though it looks like a normal two-color composite. With the manual techniques, you cannot cover this much amount of area. This picture is probably captured by satellite like QuickSat or some other satellite, or it is an airborne photograph. Even airborne photographs falls under this technique called remote sensing, airborne remote sensing. So this photograph is nothing but a product of remote sensing, where the observer need not go to this particular mountain or this water body present over here. So we are simply present in we are simply arranging that sensor to a platform, and this photograph is taken. Then this photograph is studied to demarcate different glacier zones. So here you can see this is very bright in color. This is very bright in color, and this indicates snow is very fresh, and good amount of reflectance is good amount of reflectance is being absorbed by this area. Hence, it falls under accumulation zone. And here, if you see some amount of dull tone, here you can see, because this in this region water is being melted, because of which some amount of absorption is happening here in this area. That's why this region has some darker tones, and those darker tones are present in the form of thin lines, which indicates the melt water movement in this area. So this one's the ablation zone. Ablation zone indicates the area or region where this glacier is being melted. So this is a remote sensing image again. So you can clearly see this cyan color, it indicates accumulation area, and this dark blue color, it indicates ablation area, and this region indicates the intersection between ablation and accumulation area, which is a snow line. Above which this is a snow line. Snow line is the altitude above which the snow is in the state of solid, and below which the snow slowly converts into the liquid form. And further, another application of remote sensing is glacier mass balance. So how much amount of ice is accumulated in the glaciers? This is a very important thing, because glaciers contribute to so many perennial rivers also, and for applications like water budgeting and weather and climate forecasting applications, and also to forecast the disasters and etc. We require to study this glacier mass balance problem. So this glacier mass balancing can be done with help of DEM differencing. DEM means digital elevation model, which is again a product of remote sensing. By retrieving digital elevation models in different time frames, and by subtracting these digital elevation models, we can calculate how this glacier mass is changing. Another technique is area accumulation ratio and ELM method. ELM is the equilibrium line of altitude. So area accumulation ratio is nothing but the amount of area that is under the zone of accumulation. It is nothing but the ratio between amount of area that is under accumulation to the total area of a glacier. A regression model will be developed between the altitude of snow line and the amount of area that is under the amount of area and the area accumulation ratio, and this model will help us to study about the glacier mass balance. And further, we have satellites such as GRACE. So GRACE is nothing. GRACE is a twin satellite experiment where uh, these two satellites move with a certain distance in between them, depending on how the glacier mass is changing. Glacier mass is, sorry, depending on how the Earth mass is changing, the distance between these two twin satellites is going to alter. So why this altering happens is because there will be change in gravity because of mass changes. So with help of this gravity experiment, it is possible for us to study even glacier mass balance, and different snow physical parameters also can be studied. And next application is glacial lake outburst. So we study different aspects of lake outburst, like what is the volume of lake, and how much amount of water is present in the lake, and what is the density of snow surrounding the water body, so snow surrounding this particular lake, and how it is changing with time. By observing all these things, some type of applications can be worked out, and we can do probably get some important information that is related to the glacial lake outburst. And snow avalanche detection. So it is possible for us to alert uh, avalanche prone regions, but with help of the data that is acquired using remote sensing. Because we talked about snow density, snow thickness, snow water equivalent, so many parameters earlier. These parameters can be estimated or can be monitored with help of remote sensing data, and all these parameters are very essential for identifying the areas which are under the danger of, which are prone to avalanche. So avalanche detection can be carried out. It is another application that is that can be carried out with help of remote sensing in the area of cryosphere. So I would like to conclude my presentation here. Next is a case study, but I would like to conclude here. So these are all some of the presentations that can be carried out with help of remote sensing data in the field of cryosphere. So thank you. And if you have any questions, I would like to take. Thank you.
Thank you very much, sir, for your wonderful presentation on the emerging research area in remote sensing and GIS. And thank you very much for spending your valuable time with us. Thank you, sir. From student perspective, is there any queries? No questions? Okay. Thank you, sir. Thank you very much.
Okay, thank you. Thank you.